I'm Antonio Sala, and in this video we're going to solve the partial differential equations arising from modeling this tubular heat exchanger whose inputs are inflow with a given input temperature and heating power Q. We'll solve the PDE assuming input flow is constant to avoid nonlinearities due to its product with temperatures, and we'll solve it with the Laplace transform method on the time-dependent side. The partial differential equation we are going to solve, it's this one. Details are in other materials, it's well known. Bar Q is the heating power per unit length, F is flow, S is cross-section, rho is density, and capital CE is specific heat, and bar kappa is the heat transfer coefficient per unit length. If the pipe is perfectly insulated and there's no heating, then we get the famous transport equation. And if time derivatives are set to 0, we also get the famous steady-state equations, which are ordinary differential equations in the x variable, yielding these exponential profiles in length. Of course, our goal is solving not only steady-state, but also the transient, so that we will get this transport delay and this stationary regime as particular cases of our more general solution temperature function of the position in the pipe and time. So let us discuss how to solve this PDE, which is exactly the same, but in order to avoid clumsy notation with lots of physical coefficients, we have just named as V the transport velocity and A and B the coefficients that multiply temperature and heating power, so we shorten notation for further developments. As we said, we want to find a temperature function of both position and time that solves this partial differential equation. We are going to use Laplace transform only on the time domain, let's say. So we use Laplace transform in the usual way that we control people are accustomed to do. So Laplace transform of the time component will be just this integral, as usual, in which x will be considered just constant when we are dealing with this integral. So we get some t in black bar font representing the Laplace transform of the time component at each different position. So we have one Laplace transform for each position in the pipe, so the Laplace transform of temperature here will be of course different to the Laplace transform of temperature here, and Laplace transform will of course encode the time dependence. The next important step is realizing that we have the time derivative, but we have the space derivative. So how do we get the Laplace transform of this? Well, fortunately, as x does not take any part in this integral, we can easily realize that if we take partial derivatives with respect to x in here, this amounts to just taking partial derivatives to this function of x inside the integral. Of course, formal proofs are more complicated with limits, etc., but it seems common sense because x is not the variable involved in the integration. So the Laplace transform of the spatial derivative is the spatial derivative of the Laplace transform. Remember that Laplace transform refers to time domain. Good. Then this is in a generic abstract notation what we are saying here. So we can take Laplace transform now easily. This term will just be the Laplace transform of the heating power that can depend, of course, on position if we have an irregular heating with different power per unit length at different positions of the pipe, but later on we will remove the dependency of x, assuming uniform heating power along the pipe, but for the moment being we can leave it as this. Then AT, of course, Laplace transform is just AT. The thing we had here, the Laplace transform of this spatial derivative, is the spatial derivative of the Laplace transform. And finally, this is the usual bit in control. The Laplace transform of the time derivative amounts to multiplying by s the Laplace transform and subtracting the initial condition for time equal to 0. Remember that we have a different Laplace transform for each position, so we can have a different initial condition for each position. So this is a standard time domain Laplace transform where x is assumed constant. So moving things a bit, we get this expression as the Laplace transform of the partial differential equation, understanding Laplace transform in the time dimension. We can go on. The trick of Laplace transform is that now we need to operate with letter s algebraically, just as if it were a number. So this is now an ordinary differential equation because we are taking derivatives with respect to only one variable, and a, b, v, s need just being considered just as a plain algebraic variable doing sum, multiplication, etc., and not differentiation. This will be the key aspect for solving this. However, for simplicity, we will now remove the dependency on position of the heating power, uniform heating. I mean, we don't need to. We can solve the equation with more complex heating profiles, but okay, let's keep things simple. If you want some complication, I leave it for you to think on it. And also, initial condition, this is how the temperature profile inside a pipe is at time 0. As my goal is just obtaining transfer function representations, because that's what control people we are used to, then transfer function representation don't need to worry about initial conditions. So I'll set this to 0, again for simplicity. Barq is an input and initial conditions are also known, then this is in a generic term, a known function of x and s, so we can do the same things we'll do later, but to keep things simple, we will just consider this particular case of 0 initial conditions and uniform heating power throughout all the exchanges length. So let's concentrate on solving this equation, in which this is the most important idea, considering that s is an algebraic variable. I am not taking derivatives with respect to it. Then this is an ordinary differential equation in which, okay, we take derivatives with respect to just one variable. So this is, in simple terms, something similar to this. This is p, some numbers that do not depend on x. This is h, some numbers that do not depend on x. So if we know the solution to this, we just can replace p and h and solve it. And okay, this is the first order differential equation that you see in every introductory course on differential equations or every introductory course in control. And we know this exponential formula. This is the well-known free response, exponential decay, and this is the forced response, the 1 minus exponential times the final value, which is setting these derivatives to 0, h over p. So once we realize that the solution to this is this, and that p and h in here do not depend on the letter x, then okay, bam, we found the solution to what we want, just replacing here the values of p and h. This is it. And the only thing we now need to consider is that, okay, we didn't have the inlet temperature input in our equation, but that was a boundary condition that we get here. Because, okay, this initial condition, if we are dealing with a different t of x for every s, then we get a different t of 0 for every s. This 0 refers to length, because these derivatives are taken with respect to length. So the temporal domain is just the s argument that we were neglecting here, but we added here because the solutions will be different for different values of s, considering s to be a number. Okay, that's the trick of Laplace. Okay, we operating here as if s were number 3, 4, 5, something that can take some numerical values, algebraic operations with it, even if we know that there is something very important about its relationship with time domain. But with this Laplace method, we have sort of decoupled. In time domain, we consider x to be a constant in the Laplace transform integrals. And now in space domain, we consider s to be a constant in the space domain differential equations and associated solutions. So this is finally the form we are searching, and we have almost finished, because this is actually the Laplace transform of the time profile of the temperature at position 0, which is by definition, position 0 is the left side of my heat exchanger. So at x equals 0, we are assuming that temperature is the inlet temperature. So this is the Laplace transform of the inlet temperature. Hence, we can replace it like this. So our transfer function representation of the solution to the partial differential equation is finished. This is the transfer function that multiplies the input inlet temperature. This is the transfer function that multiplies the heating power per unit length, assuming uniform heating, constant power per unit length along all the pipe. Note that we have a different transfer function for each x, because indeed the transient will be different from x close to the left or x close to the right end, let's say. What do we observe in this expression? Well, if we factorize the exponential of the sum as the product of two exponentials, then the pure exponential of s times some number is the Laplace transform of a delay of x divided by the speed of the flow. Indeed, the changes of input temperature, if the flow is circulating, let's say at 2 meters per second, then a point 2 meters away from the inlet will receive that changes 1 second later. So that's it, 2 divided by 2. In general, this is a delay saying that the effects of the input temperature will be felt at position x with a delay that is proportional to the length of the pipe that the fluid has to cover to reach that position. This is, of course, coincident to what intuition would expect about the transport delay. The further away we are from the left side, the longer it will take for hotter or colder inlet temperature to be felt by a sensor at that position. The second term, this thing is an exponential decay due to the heat conduction to the outside as length progresses. From the inlet temperature, if heating power is 0, it will be progressively decaying with this exponential term in length, and also, it will be felt with a particular time delay, as this other term explained. So the solution with respect to the input temperature is similar to this stationary steady state temperature, but the transient adds a delay effect to this exponential decay. Of course, as the gain of a delay is 1, then once the delay time has elapsed, then we get this stationary value. And then we have also this transfer function of the effect of the heating power that, okay, well, it's kind of, again, we have sort of delay and exponential decay plus like a first order heating of a tank due to heating power. We'll carry out numerical simulations later on in other materials. It's important to see that if we want to get steady state, once we are in transfer function, Laplace domain, we need to set S to 0. So we get equilibrium temperature equal to transfer function gain, which is setting S to 0, times the equilibrium input. So if I put some constant equilibrium values and I set the Laplace variable to 0, then I get this steady state solution, which is this expression that coincides with the steady state solutions, of course, of the standard heat exchanger formulas. In most technical problems, the only variable of interest to me is just the outside temperature, not the inside temperature profile. So if my only interest is in the outside temperature, I can just skip dependence on x and just replace x by the length of the pipe. So I will get an expression that it only depends, of course, now on s, because we are particularizing to a particular position, the right-hand side extreme of the heat exchanger. And then this is a particularization for the output temperature that, okay, if L divided by the speed is called phi, and I carry out some operations, I can write this transfer function matrix for the outlet temperature, in which this is the transfer function associated to heating power, and this is the transfer function associated to inlet temperature. Of course, replacing all these A, phi, B, whatever by physical parameters, I would get the actual transfer function in physical parameters, but okay, I leave it for you because the important thing is seeing what happens here in a compact notation in which we have delay terms here and here, exponential decay due to the cooling in the temperature profile, and we have first order dynamics of the heating resistor. As a last observation, all these developments are valid only for constant flow, because we had this product flow times temperatures or its derivatives that made nonlinear if both flow and temperature are allowed to change. So in that case, we will need to linearize this product as the nominal flow times the partial of the temperature with respect to the position. Now temperature will be an incremental variable around a certain operating point, plus the true flow times the derivative with respect to x of the temperature profile in a given operating point, which surely will be sort of exponential or like that. So carrying out the Laplace transform method in this new equation would be needed to approximate the transients due to flow increments with respect to a given operating point of the flow. Again, this is not considered in this material for brevity. So we've finished. Let us summarize. In this video, we have reviewed the partial differential equation that governs this tubular heat exchanger, a pipe with a resistor along it, and we solve it via the Laplace transform on the time domain component of the solution, as our goal was just obtaining transfer function representations. Because we control people, we are used to them, then we have let some initial conditions to 0. And also for simplicity, we have assumed uniform heating, and then we ended with this representation in Laplace domain that if we particularize to the outlet temperature, we end up with this transfer function matrix representing the dynamics of the heating power and the inlet temperature, in which we observe delay, exponential decay as we move to the right, and first order heating dynamics. So we finish with this. Thanks for watching.